the fields in the 10-dimensional theories. So the peculiarity of these fields is that their corresponding tension here, which I should have written now, scales like G string to the -1 in the string frame, and this scaling is basically associated to the R plus weight, so to the dilaton weight that these fields have. And one can classify all the fields in the theory according to the corresponding dilaton weight. So if the tension scales like G string to the alpha, I can label all the fields in terms of alpha. So in the type 2A theory, I've got that for alpha equals 0, the fundamental 2 form. Alpha minus 1, I have all the Ramon fields. And also in alpha minus 2, I have the solitonic, the dual of B2, and also there's a dual of a dilaton, which you can introduce in your theory, on which the algebra closes. Similarly, for the type 2B theory, I have for alpha equals 0, I have again the Navier-Stokes 2 form. The Ramon fields are C2, C4, C6, C8, and C10. And then these two objects form a doublet of SL2R. And similarly, there is a doublet of SL2R here, which is made by C6 and D6. And the 8 forms form a triplet of SL2R, which splits in terms of alpha in a field with alpha minus 1, which is C8, a field with alpha minus 2, and a field with alpha minus 3. As you see, I'm labeling the fields like B, C, D according to decreasing value of alpha. And finally, if the 10 form belongs to a quadruplet of SL2R, which splits in this way in terms of alpha. So you can ask how many of these fields are associated to branes by simply using our rules here. Yeah.
Where is this 8 and 10 split coming from? Is it
8.
These fields, D8, 8.
Okay, so the 8 forms, so the theory has an overall SL2R symmetry. And the fields group in representations of SL2R. So the dilaton weight is an R plus inside this. So the 8 forms belong to the triplet of SL2R, which splits in these three fields when you decompose the SL2R respect to R plus.
I was just asking, what are the D and E fields? How are they defined?
Oh, these are fields these are fields on which on all these fields the supersymmetry algebra and the gauge algebra closes. So you can introduce additional, for instance, this object will be object with no field strength at all, but still you can introduce, probably I should write them down in terms of SL2R. So this will be an A2 alpha. Alpha goes from 1 to 2. These are the 2 forms. There is a singlet A4. Then these are the duals of these guys, of the 2 forms of the type 2B. And these 3 guys are basically the duals. This will be the symmetric alpha beta, which is the 3 of SL2. And this will be basically the duals of the scalars in the theory. So there are 3 objects, out of which one field strength is 0, put to 0 by A. But this will be a quadruplet of Okay, so, well, probably I can do it here. So let's see how our rules work. For instance, let's go. So we know that all these objects are we have already seen that all the Ramon fields are associated. All these objects have a corresponding brane. Let's see what happens, for instance, for the D6 of type 2A. So we write down all the most general gauge invariant Vezumino term, preserving the charge alpha. So basically what you have to do, given the Ramon field C, say Cn, you have to introduce volume field Cn minus 1 such that basically the corresponding field strength, volume field strength of this guy will be dCn minus 1 plus the pullback of the Ramon field. It's exactly as we did for the fundamental fields when we were writing down the Wetzel-Theorem for deep branes. So for D6, the most general object you can write down, and I won't be bothering about coefficients because I mean the rule is whatever terms can appear will appear with non-zero coefficient. So this will be a C5. There will be a C5 G1, where you see there is a G1 associated to C1, plus say a C3 G3 plus C1 G5. This corresponds to a volume field C0, this to a volume field C2, and this to a volume field C4. But now we are in 6 dimensions, and so I should add a rule here to our set of rules, which is we are assuming that there is a democracy on the bulk, but there is also a democracy of fields and dual fields on the volume. Therefore, we are in 6 dimensions, and in 6 dimensions, a zero form and a 4 form are dual, so this counts as just one scalar. And C2, because of democracy, C2 must be dual to self-dual, was dual to itself. Therefore, this theory is propagating on the volume a self-dual 2 form, one scalar, plus we are in 10 dimensions, so this is a 6-dimensional volume. There are 4 additional scalars, which makes one self-dual tensor plus 5 scalars, which is a tensor multiplet. So this is a supersymmetric brane. If you repeat the same game for this guy, you'll find that this is object is not associated to you can't make the whole volume degrees of freedom fit inside a supermatrix. So this object will never be associated to a supersymmetric to a supersymmetric half PPS supersymmetric brane. If you do the same for the most worst for the D6 of type 2b, you'll do the same here. So you have D6, but now the fields are C4 and C2. So this will be a C4 G2 plus C2 G4, which correspond to C1 and a C3, which are dual to each other, which is a vector. So you have one vector and 4 transverse scalars, which is a vector multiplet in 6 dimensions. So this object also is a nice brane. And if you repeat the game for all these guys, you'll see that this object and this object will be your branes, the branes of your theory, while you can't define you can't associate a brane to these guys here. So this basically completes the picture in 10 dimensions.
Sorry, if I can ask.
Yeah.
You're saying you cannot define a brane associated whenever the field doesn't admit a supersymmetry multiplet.
Yeah.
Right? But
I
mean, couldn't there be a non-supersymmetric brane at weak coupling?
There could be a non-supersymmetric brane. There could be a bound state of branes. Yes, I'm just looking at this particular sector. I'm just looking at the fundamental branes.
But somehow you're saying that when there is a supermultiplet, then there must be a brane associated.
Yes, that's the rule. Okay. That can be that's what I'm assuming, yes. Okay. So let's go to lower dimensions. So let's go. So this is our rules. So let's go to so let's go to any dimension. So let's go to lower dimension. Say D, and so what I need is the notion of what is alpha in this case. And of course, what I have to do here is that I know that this theory, these are maximal supergravity theories. So these theories have a U-duality, symmetry. And what I want to do is to is to decompose the fields which are in representation of U-duality with respect to T-duality, which is SO dd times R plus, which is always what happens. And sorry, small d is 10 minus d, where d is the space-time dimension. So the idea is I know, well, this is the representation of all the fields, including these non-propagating fields, which are the equivalent of, say, C9, C10 of the 10-dimensional theory, are known in any dimension. So I decompose these objects with respect to T-duality, and this object here will be basically, T-duality is a perturbative symmetry of string theory, so this object will be the weight with respect to the D-dimensional dilaton. So the weight associated to this R plus symmetry will be the equivalent of will be our alpha there. And so what do I get? If I do this, I get that the fields of the low-dimensional theory group in a very universal, in a very universal way. Particularly, alpha equals 0 objects are simply a 1 form in the vector representation of SODD and a 2 form. The Ramon Fields in the D-dimensional theory are spinor representations of SODD, which are either of one chirality, which we denote with A, or the opposite chirality for either even, according to the rank of whether the rank is even or odd. Also, the alpha minus 2 fields, so the equivalent of the solitonic fields, which are the equivalent of the D6 up there, have a very universal form in the D-dimensional theory, which is there is a D minus 4 form, which is dual to this guy. There is a D minus 3 form in the vector representation of SODD, which is the dual of this guy. And then there is an object in the D minus 2 form in the adjoint, AB, in the adjoint of SODD, and then D minus 1 in the antisymmetric with 3 indices, and a space-filling form with 4 indices antisymmetric. I should probably point out that whenever this object is, any of these objects is 6, so for the dimension in which any of these guys is 6, the corresponding representation of SODD splits in self-dual and anti-self-dual. Well, we can do an example here. If D is 4, then we are in 6 dimensions. And for that, D6 is with 4 indices, splits in the self-dual with 4 indices and anti-self-dual for each. This will correspond, as we will see, to the fact that this phi brane can either be a vector, can either support a vector or a tensor matrix. Okay, so let's see how we can say write down Vezzo-Mino terms for all these objects. Well, let's start with the fundamental objects. B1 can go down. So let's start with these guys. So, okay, the most general object we can write down is simply B2 plus B1A F1B eta AB, where this is the invariant, the metric of SODD, and F1A is B0A plus B1A. So we have given B1A, the bulk field B1A, we have introduced the corresponding volume field, which is a scalar in the vector of SODD. Okay, if we want to count now the degrees of freedom, of course I have, say, D minus 2 transverse scalars, because this is a 2-dimensional volume in D dimensions. And then I have 2D scalars coming from this object here. But this is, of course, far too many, because I just want 8 in total. But this is, this is D, this is 10 minus D minus 2 plus 2D. So this is 8 plus D. So I have D too many. And the reason, we know what's happening here. What's happening is that this is, well, okay, we can simply look at our rules, which is we want democracy on the Wald volume. This is a 2-dimensional Wald volume, and I can simply impose a self-duality on B0A. So this B0A is self-dual. So it's related. Okay, so half of the degrees of freedom are basically magnetic. So what I have to do is just divide this by 2, and this is indeed the right counting. This is, of course, something we all know from say, double string theory on a double torus and so on. But as we will see, this generalizes to all the other cases as well. I can already immediately mention here what we mean by wrapping rule. If you count now the number of branes, of course, I have 1 branes and 0 branes. So in type 2b or type 2a, so let's say this is type 2a or type 2b, always have 1 brane. Either, I have B2, these two objects here. So in 9 dimensions, I have 1 here, as usual. So in any dimension, I have one string and 2D, say, 2D particles. So this is 2, this is 4, 1, this is 6, 1, this is 4, 1. And you see that what the wrapping rule means is that for fundamental objects, a brane, so a wrapped brane, so a brane, when it's wrapped, yeah, you see, gets doubled. And when it's unwrapped, it's just not undoubled, and it's just multiplied by 1. So you see, for instance, this guy here comes from 4 plus this brane double. So it's 4 plus 1 times 2, which is 6. Of course, this is something we all understand from, well, if you want, from, well, the reason for this is very simple. It simply says that in the lower dimensional, starting from B2, if you go to the lower dimension, then not only B2 contributes to the vectors, but also the metric. So you have an additional contribution each time you compatify on a circle coming from the PP wave. So you have an additional particle, but then people think about this in terms of the double torus. So you can, in principle, think. You can think of you can think of this fundamental string as either unwrapping or wrapping a double torus. So each time it wraps, it basically sees that twice as many. Twice the circle, basically. Okay, so let me keep going this way. So this is so as far as the fundamental objects are concerned. But let's see what happens for the D branes, for instance. And then we'll move to the solitonic branes. So for D branes, the D branes, as we said, are in spinor representations of SODD. And therefore, to write down the corresponding Versumino term, we need the gamma matrices of SODD, which are simply defined by gamma A, gamma B is 2 ether AD, AB, and the D brane effective action has a very, this Versumino term of the D brane effective action has a very natural, say, a compact formulation, which is similar to, which is the generalization of the 10-dimensional case, which is simply e to the F2, e to the F1A gamma A C. So for each Ramon-Ramon field, you pick up, the corresponding rank, and you expand this exponential, keeping these gamma matrices here. So how let's count the degrees of freedom again. We have one vector here from F2. Then you have B0A, which are the scalars, and then you have the transverse scalars. But again, this is far too many scalars, because this is, again, 2D scalars. The transverse directions are again, say, 10D minus P plus 1. And so you get this, you want this to be, you want half of many scalars here to make the counting, for overall counting of the scalars right. But now we are in a P plus 1, we are taking the P plus 1, we are taking, consider, a P brane. So this is any P. So now we clearly cannot impose any, in P plus 1 for volume dimension, we can't impose any self-duality on the scalars. So how can we possibly get rid of half of the scalars? And the answer is, you simply have to look at the gamma matrices here. So if you look at the gamma matrices, you realize that, well, these are the gamma matrices of SO. So let's take an example which is D equals 8, which is SO22. then you write down the gamma matrices of SO22, which is basically up to some factors I are the gamma matrices of SO1, 3. And then if you write down gamma, say 1 plus, which is gamma 1, say 1/2 gamma 1 plus, say, gamma 4. Well, I probably should write them down, but these are simply, so gamma 1 is, I consider gamma 1 as 0, 1, 1, 0. And gamma, say, gamma 2 is 0, sigma 1 minus sigma 1, 0. And then gamma 3 is 0 minus I sigma 2, I sigma 2, 0. So 1 and 3 are the redirections, say, plus, and 2 and 4. Two and 4 are the direction minus here in SO22. So if you write down, for instance, gamma 1 plus, which is in this light-like direction, gamma 1 plus 4, you realize that this object is the following matrix: 0, 1, 0, 0, 0, 0, 0, 0, 1, and 0. And similar structure you find for all the other light-like directions. So what's happening? What's going on here? For each light-like, so I probably should write down gamma 1 minus as well, which is 0, 0, 0, 0, 1, 1, 0, 0, 0, and 0. So you see, let me write down an explicitity of S0 for instance, when in 8 dimensions we are taking 3 branes. So this is D3. So this is a 4-dimensional Ramo-Ramo field. So the term will be C4A dot plus F2 C2A dot plus F1A gamma A dot A C3A plus blah, blah, blah. And you see that A dot is fixed. So for each fixed A dot, you see that this corresponding line here is only 0 for either 1 plus or 1 minus. And this is the same for all the other light-like directions, and this generalizes to any dimensions in SODD. So, which means that basically, it is if you project on the light-like directions, you halve the number of scalars by simply, with this mechanism. So it's really the gamma matrices which are taking care of reducing half of the scalars. And the counting is again right. So how many D-branes do I have? Well, okay, I can do it here. So, okay, the D-branes are then in chiral representations of SODD, which makes 2 to the D minus 1 branes in each dimension. So you start with, say, 1, 1, 1, 0, 0, 1 in type 2A, type 2B. This is, you jump the rank of the number. So this is either, so for instance, this is C1, this is C2, and so on. In 9 dimensions, you get 1, 1, 1. In 8 dimensions, you get 2, 2, 2, and so on. So in each dimension, the corresponding brane can be seen as either. So for instance, here we are talking about the 1 branes. So you can see the 8-dimensional 1 brane as either a 1 brane which is unwrapped in 9 dimensions or a 2 brane wrapped in 9 dimensions. And to get 2, you simply get multiplied. I mean, you simply add up the branes. So basically, the D branes have a trivial wrapping rule. So they just don't. Whatever you do, you don't double. They just multiply by 1. So basically, the D branes don't see the double torus somehow.
The branes at angles when you wrap it in angles.
Well,
because, okay, you basically use one volume in the space.
But an angle with respect to the other, I mean.
So what you do, let's suppose you wrap at an angle, then how you see it?
Well, I think they won't be a half BPS. I'm really talking about single branes. I'm talking about single brane.
There are half BPS.
But in the maximal.
Yeah.
But an angle with respect to.
I mean, you basically, if I remember well in the past, people used to take to, a wrap along the volume or wrap on the transverse spaces, then you reduce, and I think those that will count for you all you have. But then, of course, there were other kind of funny rules where you wrap, you took the kind of cycle, which was not exactly the volume, not exactly as the transverse space, and you wrap somewhere in the middle. And still preserve how the supersymmetry.
Yeah, but this is this is on torus. I don't see. Okay. No. Okay. But
kind of dionic and two branes and so on. How do you
but you don't. These are single branes, so these are not never bound states of any.
They still come from wrapping.
Well, yes, but they don't come from this count, from this analysis. So again, all these branes can be seen as coming from the 10-dimensional branes using our wrapping rule. So let's move to the main subject of the talk, which is these objects here. I can write them here. So suppose so again, let's do the example in 8 dimensions. So in 8 dimensions, D is 8. So the first object we consider is the 4 form here. So a 4-dimensional, so a 3-brane, a 4-dimensional Wall volume in 8 dimensions. And to write down the action, you need to introduce also the C matrix of SODD, which has this block diagonal form. A and A dot, of course, are the chiral left and right indices. So the effective action will be C3A, the Wall volume field strength G1B, plus C1A, the Wall volume field strength G3B, multiplied by CAB, plus GC2A dot, G2B dot, CA dot B dot. So let's see what you get here. Now these objects are 2 by 2 matrices, so you get 2 scalars here, two forms here, which are dual to the scalars because we have a 4-dimensional Wall volume. So you got 2 scalars plus 4 transverse scalars because we are in 8 dimensions, as this is a 4-dimensional Wall volume. And this is a vector. This is actually 2 vectors, but again, using our, say, democracy rule down there, this makes, using dualizing, you relating these 2 vectors by self-value electromagnetic duality, this makes 1 vector, which again is a vector multiplet in 4 dimensions. What happens for so these objects are basically branes. What happens to D5? So D5 is in the vector of SODD. So this is the vector of SO22, and this you can write down the Vezzo-Mino term as C4A dot G1A plus C3A G2A dot plus C2A dot G3A plus C1A G4A dot. Times, there is a gamma matrix, so there is a gamma matrix CA. This A index will be a gamma matrix, and there is an A dot here. And then we can also write down the term which is D4. I still have I write down all the possible terms, so I write down the term which is D4 F1A. So A is fixed, and let's count the degrees of freedom here. So here I have 1 scalar. So 1 scalar plus 3 transverse scalars, because this is 5-dimensional Wall volume in 8 dimensions. Then I have these are 2. This is a scalar with an index A. This is a vector, and this is a 2 form, and this is a 3 form. Okay, we are in 5 dimensions, so these objects are supposed to be dual, and so are C0 and C3. But still, this is far too many because this is the index A goes from 1 to 2 for SO2, 2. But again, so to have the counting right, again the gamma matrices are to the rescue because the gamma matrices come to the rescue because again I'm assuming here that these directions are like-like directions. So these directions are either, say, in this notation, 1 plus minus or 2 plus minus. If I do this, I look, for instance, at this matrix, and you see that these objects have non-zero entry only for one of the two chiral directions, no matter what you do. So if you take like directions for A, so only in the like directions you have supersymmetric branes, because out of these objects you project away half of the chiral directions in all cases. So we have already learned something here. So the supersymmetric branes are in the like directions. So now let's move to the next guy, which is the 6 forms in 8 dimensions. Okay, so this will be the write down more general Verzomino term. So this will be D6AB plus, well, this will be C5A G1B plus C3A G3B plus C1A G5B times C gamma AB in the direction block the left the chiral block plus C4A dot G2B dot plus C2A dot G4B dot times C gamma AB A dot B dot. C gamma AB is block diagonal, like exactly as the symmetrics. And finally, I can write a term which is D5A F1B. So let's count how many. Let's count the degrees of freedom in this case. So we are in 8 dimensions. So I have 2 transverse scalars plus 2 scalars coming from this term, because this object can either be the index A or the index B, which are different. So this makes 4 scalars. Then I have, I have a C0 here, a C2 here, a C4 here. So these 2 objects are dual, and because we are in 6 dimensions. Then I have a C1 and a C3, which are again dual. But again, if I simply count the spinor components of this guy, I simply get far too many fields. So what's actually going on here? Well, to understand what's going on, let me write down a particular component of this matrix here, which is C gamma AB. So let me write down the matrix gamma 1 plus 2 plus. And this turns out to be the following matrix, which has non-zero entry only in one term. And I can tell you that this happens for all these directions. In particular, this happens also for the direction 1 minus 2 minus, which also has a non-zero only in this block. 1 non-zero in this block. And for the other 2 directions, the direction I'm going to define, which have 1 plus 2 minus and 1 minus 2 plus, which have non-zero only in one component on this block and another component on this block. So what you see is that not only these matrices now are projecting on half of the chiral spinors, but they're also projecting out the opposite chirality objects here. So in other words, if I take this direction or this direction, what happens is that if the objects, so this term drops out, and this term is halved. So what I get is just out of 2 vectors and 2 dual vectors, I only get projected out. I only get 1 vector, and I get 1 vector plus 4 scalars, which is a vector multiplet. So these directions correspond to a vector multiplet. If I instead take these directions in this T-duality representation, and I should probably mention that these belong to the self-dual part of gamma. This is SO2 too, so I can impose a self-duality condition on this on the antisymmetric with 2 indices. And these 2 directions are, say, self-dual, and these 2 directions are anti-self-dual. So they belong to 2 different representations of SO2, 2. But so if I take these 2 objects, then this guy is 0. And what I'm left with is 1 scalar plus the dual, and C2, which is self-dual. So I get a tensor brane supporting a tensor multiplet. in the other directions, which is, well, I still have other two directions in this representation, which is, say, gamma 1 plus 1 minus and gamma 2 plus 2 minus. In these directions, I do not get any brane. The counting simply doesn't work. And this is completely general. This is completely general in the sense that for any, say, representation of T-duality, which corresponds to A1, AN antisymmetric indices, I split this in, say, in light-like direction. So I for each index, I go to a light-like basis in which the indices are n plus minus. For n goes from 1 to d. So each of the objects goes from 1 to 2d. And so this object A1, AN, the only branes are in the directions, say, M1 plus minus N, NM plus minus, with each of these guys different. So you never get something like this for any direction. And let's count how many branes. Let's count the number of branes. Okay, this is 2D choose M, say, represent dimensions, the dimension of the representation. But these objects are D choose M times 2 to the M, because for each of these objects, I can choose the signs. And now I can count the branes. Okay, remember we started in 10 dimensions. We only have a 5 brane in 10 dimensions, 5 branes. So we either have 1 or 1 according to whether we consider type 2A or type 2B theory. In 9 dimensions, this becomes D5. Sorry, should look here. In 9 dimensions, this is a D5. So this is a 4 brane. So I've got a 1 here, and this is a D6. The symmetry is SO1, 1, and therefore this vector splits in self-dual and anti-self-dual. So this is 1 plus 1, either a tensor multiple or vector multiple. If we go to 8 dimensions, and by the way, well, that's of course the end of it, because I don't have this representation for SO1, 1. Well, I mean, I do have this representation, but I don't have any light-like directions according to this rule. I can. This is only, for SO1, 1, this is only 1 plus 1 minus, which is exactly what I'm drawing out. If I go to 8 dimensions now, this object is a 3 brane. This object is this is a this is a vector of SO2, 2. And this is the one that we just considered here, and we got 2 plus 2. According to this rule, and then of course I split in irreducible representation. So this will give me 4, but then I take self-dual and anti-self-dual, and this is 2 vector plus 2 tensor branes. Then I do it in 7 dimensions. This will be a 2 brane, a singlet 2 brane. This is a 6. Now, if you do this counting for D equals, so this is SO3, 3, so D is 3, and M is, for this guy, M is 2. And I get 12 here. And then I get 4 plus 4 vector plus tensor branes. Now we see here that for any of the, well, we can do the next one. I can give in 6 dimensions, it will be 1, 8, 24, 32, 8 plus 8. First of all, you see here immediately that according to this rule, there is never an object which is higher than a 5 brane, which is consistent to the fact that in 10 dimensions only have I have solidonic 5 branes. So all these objects can be seen in principle as coming from reduction from the 5 brane. And you see that, for instance, if you take these 24, say, 3 branes in the 6-dimensional theory, you can count them as coming from either this brane doubled, so 6 becomes 12 branes, and the wrapped brane non-doubled. So basically, the wrapping rule in this, and this is completely general, so the wrapping rule in this case for solitonic branes says that if you wrap you undouble, so the wrapped brane is simply multiplied by 1, and the unwrapped brane is multiplied by 2. Which, if you remember, this is exactly the opposite of the wrapping rule for the fundamental branes. And so starting from this initial condition, if you want, the number of solitonic branes in 10 dimensions, using this wrapping rule, you get all the solitonic branes in all dimensions. And you see that this is not simply, okay, probably I should say that this is exactly the opposite as the wrapping rule for the fundamental branes. But this is, of course, as far as these branes are concerned somehow, this is absolutely, say, natural, because these branes are exactly the dual of the fundamental string and the fundamental particles. So you would expect a wrapping rule which is exactly the opposite. And indeed, you would expect that the objects that contribute to these branes are either the NS5 or of the Kaluza-Klein monoball, which are the dual of the fundamental string and the PP wave. But there is something more here than that, because this rule applies also for these objects which are highly, say, non-standard in the sense that they are, for instance, well, this object is space-time filling. So there's more to this rule, to this wrapping rule, than simply say that this is the dual of the wrapping rule for the fundamental objects. And of course, it will be, and again, this wrapping rule is very simple. So this counting algorithm, which is very simple, comes from projecting away here lots of components of these T-duality representations. So it's really something very, very, so it was very, very, well, when we found it, we were quite excited, to be honest. So I should probably also mention that if you go to, say, more solitonic branes, for instance, if you go to alpha minus 3, also the fields with alpha minus 3 have a completely general expression, which is E d minus 2 A dot. So this would be, well, I mean, there was a guy like this in the type 2B theory, indeed. But it's also E d minus 1 A dot in the irreducible, say, Gravitino representation of T-duality. And finally, there is a space-filling object in the representation AB, antisymmetric A dot. So this is the sort of tensor spinor representation, irreducible. And these representations are, well, of course, are what they are. But then if you do the same trick here, so you select inside each of these representations the components which fit these rules and for which you can write down a supersymmetric brane, you realize that these alpha minus 3 branes satisfy a wrapping rule, which is whatever you do, so wrapped or unwrapped, the branes are in both cases are just doubled. So out of, I mean, these dimensions, of course, you don't see this doubling in the dimensions of these objects because, of course, they don't satisfy any sort of wrapping of simple rule like this whatsoever. But then, if you just count the number of branes, and you count the number of branes according to this, I mean, you put the number of branes in this table, you see that you can get the d minus 1 branes from the branes in d minus 1 dimensions from the branes in d dimensions by simply using this wrapping rule and starting, if you want, from the 10-dimensional initial condition. If you go to more solitonic objects, so we know that there is also an alpha minus 4 brane, which is a space-filling brane in 10 dimensions, in type 2B, then these alpha minus 4 branes are associated to fields, which we call F according to this way of labeling, which are FD, so space-time filling fields in the representation A1, AD of SODD. So D in this is completely antisymmetric and self-dual in T-duality space. I mean, the irreducible representation self-dual, the antisymmetric indices. And for these objects, again, I mean, these are space-filling branes, so this object can only wrap. But for this object, again, you see another wrapping rule. So as far as 10-dimensional, and this is all about, this completes the story as far as the 10-dimensional branes are concerned. So basically, because as I said, the S-dual of the D9 is exactly in this category here. So as far as the 10-dimensional type 2A or type 2B branes are concerned, they all satisfy a sort of wrapping rule like this, which we found, I think it's worth understanding better. But then this is not the end of the story, because starting from alpha minus 4 and going more non-perturbative if you want, starting from 7 dimensions, there will be branes which simply, for instance, in 7 dimensions, there will be an object f d minus 1 in the representation a1, a d minus 3. So if d is 3, which is 7 dimensions, this is a singlet of T-duality, and this is a 5 brane in 7 dimensions. So starting from 7 dimensions, you see branes in the theory which cannot relate in any way whatsoever to the 10-dimensional branes. I can also say, just to conclude, I can also say something about the solidonic branes again. In terms of, you can obtain all these branes in the, so you can obtain all these objects in the lower dimensional theory by simply starting from 10-dimensional fields, which are the D6, and adding to D6 are the additional fields which are mixed symmetry. So this, I'm adding these objects just for the, at the moment, just for the sake of, I want to get these objects in the lower dimensional theory. So we know that for instance, we know that this object in 9 dimension corresponds from the type 2A theory, for instance, or the type 2B theory, as considered the unwrapped NS5 plus the wrapped Kaluza-Klein monopole. And this corresponds from the point of view of mixed symmetry fields to adding to D6 an object which is D7-1, and this object contributes to the counting on branes only if this direction, this extra direction, you have to think of this as a mixed symmetry field really. In this representation, so this will be D6. See, only when this object is in the dimensionally reduced theory is formed, this object contributes to a brane. But actually, only when this direction, this is what in the Kaluza-Klein monopole solution would correspond to the isometry direction. Only when this direction is parallel to any of these guys here. So the only brane that you can read here is D6 ash when this is the circle direction. And if you apply this, say, what we call the restricted reduction rule, you can get all these objects by introducing the following set of fields, which is D6, D7-1, D8-2, D9-3, and D10-1, 10-4, which have the nice general structure, general form, D6 plus n from n. So let me repeat, the restricted reduction rule says only when these n indices are compactified and parallel to any of n of the 6 plus n indices here, then you count a brane in the low dimensional theory. If you do this, you get again this counting here. So you get again the solitonic wrapper rule, if you wish. And just to conclude, of course, there will be well, first of all, it would be nice to understand at the level of, if this is saying something about the underlying geometry, because of course, as I said, the fundamental wrapping rule has a natural interpretation of, in terms of branes wrapping, say, twice as many cycles, twice as many circles. But of course, this is, say, something that, this is a very, say, perturbative picture, but if you include all the non-perturbative objects, of course, this picture is, you have to sort of extend it. In particular, you have to, if you want to think about it in terms of geometry, what is the geometry that gives you this wrapping rule or whatever? And then, just to conclude, I should mention, of course, that these objects are all included in, as mixed symmetry objects, are all included in the E11. If you decompose E11 in terms of either type 2A or type 2B, and these are objects of a very particular type, as Axel showed recently in the paper last year, all the objects that are associated to branes correspond to say, E11 roots which are real. I mean, real in E11 you have in principle you have roots which are real, but also you can have alpha. I mean, the length of the root alpha square. This alpha has nothing to do with this alpha here. Alpha square is can be 2 or 0 or -2 or whatever. So if you just count the roots of 11 with that have alpha square equals 2, you get out of all the fields of 11 only the fields that you get exactly discounting here, and also discounting. You get also exactly all the branes of the theory in any dimension. And I think that's what, okay. Let me conclude. That's what I wanted to say. Thank you.
You had several branes in 10 dimensions, in 2P in particular, in 2A, that they are more than the usual ones, let's say, more than the fundamental than the branes.
Yes.
Do you have spectrographic solutions for those?
Okay, that's of course that's of course a completely different story. So when I'm thinking about these branes as really a local object in the sense where really, if you take for instance already the D7, well, if you want to consider the D7 globally, you have a problem because you can't take.
Locally, I mean, of course,
no, locally,
what about the other branes?
Well, I mean the space-time filling branes, there's nothing you can do really. So.
Yeah, but you have some others, right? Like.
But for the center branes, there are solutions. Yeah?
For the center branes, there are solutions.
For the which one?
What?
For the D7 and the dual of the D7.
I mean, how the solution looks like?
I can show you.
Yeah.
Maybe we can read that for later. Yeah.
And I guess an actual question for the imaginary roots, they are somehow associated and non-perturbative.
Oh well, of course, in principle, all these objects, when dimension reduced, I mean, a lot of these objects, when dimension reduced, will give rise to forms in the theory. So you're asking whether, well, I mean, then the problem is what happens to this extra. I mean, for instance, in that case, what about the direction 1 plus 1 minus, for instance, in T-duality space? This would correspond to some guy here, probably alpha equals 0 in E11. And some of them you can think of probably bound states or something, but then of course you need some further classification, which we haven't done.
Do we know something more other than the resonator? Do we know, for example, the full?
Well, of course, not yet. I mean, in principle, you want to write down the full. Yeah, you want to write down the full effective action for these objects. Yeah, and in particular, you want to see this duality appearing. Yeah, yeah. But we haven't done that.